Did you know that you can make radio waves without electronics? In fact, all you need is a balloon. How can you possibly make radio waves with just a balloon? Stay tuned and you will find out. Radio waves are a form of electromagnetic radiation that is created whenever a charged particle or magnet is accelerated. This means we can create radio waves simply by waving an electron or proton around. Sounds simple, doesn't it? Except we can't just grab an electron or proton and wave it around. Moreover, how do we even know that accelerating a charge creates radio waves? That's where the balloon comes in. For this experiment, we'll need a balloon, which we'll use to create the radio waves. We'll also need an oscilloscope and a piece of metal that will serve as an antenna. An oscilloscope is a device that measures voltage and plots it on a screen in real time. This allows us to see how a voltage varies over time. We're going to use an aluminium tray as an antenna, but any piece of metal will do. The tray is connected to the oscilloscope in order to measure the voltage between the tray and the ground. Immediately, you will notice that a sinusoidal wave appears on the oscilloscope screen. This wave has a frequency of 50 Hz, which is the same as the AC mains frequency. The wiring in the wall creates electric and magnetic fields that induce a slight voltage in the tray. Until we start making radio waves, this wave is all we'll see on the screen. Now let's bring in the balloon and wave it around in front of the tray. Nothing is happening, which is what we should expect since the balloon is neutral and doesn't have an electric charge. For something to happen, we have to charge the balloon first. The simplest way to charge a balloon is to rub it against your hair, which is what I'm going to do in this experiment. Alternatively, you can rub it against a synthetic fabric. Rubbing the balloon causes it to either gain or lose electrons, which gives it a positive or negative charge. Now that the balloon is charged, let's see what happens if we hold it in front of the tray and start moving it up and down. Keep a close eye on the oscilloscope. Now something is happening. We can see a momentary spike appear on the screen when the balloon is moved. Let's try that again. Once again, a spike appears on the screen when the balloon is moved up and down. The movement of the balloon is causing a voltage to be induced in the tray. If we move the balloon up and down repeatedly, we can see a new wave appearing on the screen that is synchronized with the motion of the balloon. The wave is not a sine wave, because the motion of the balloon isn't perfectly sinusoidal, but instead consists of sharp peaks at regular intervals. The peaks correspond to the moments when the direction in which the balloon is moved changes. If we start moving the balloon more rapidly, the frequency of the wave increases and the peaks are brought closer together. At first, this seems to prove that accelerating a charge produces radio waves. However, at this distance, the tray is still in the region called the near field. Disturbances in the near field don't always propagate beyond this region, which means the effect we're seeing is not necessarily caused by a radio wave. To determine whether we're actually making radio waves that can propagate over vast distances, let's move the balloon away from the tray and repeat the experiment. Once again, we can observe a spike appearing on the screen whenever the balloon is moved up and down. Despite the amplitude of the peak being significantly lower, the movement of the balloon is still detected by our makeshift antenna even at a distance. At this distance, the tray is outside the near field, which means the disturbance that is being picked up is in fact caused by radio waves that are emitted by the balloon. This experiment also demonstrates that radio waves attenuate significantly with distance. The further away you are from the transmitter, the weaker the signal is. Now that we have this experiment set up, we can also test something else. Remember that radio waves are only emitted when the balloon changes its speed or direction of motion. They are not emitted when the balloon is moving at a constant velocity. But is this true? Let's try it. The charged balloon is now moving at a near constant velocity. No spikes or waves appear on the screen, other than the sine wave caused by the wiring in the wall. When the balloon starts accelerating, the spikes start showing up on the screen again. So yes, it's true. A charge moving at constant velocity does not emit radio waves. We've been using the term radio waves rather loosely. All we're really doing is creating static noise, which is the noise that is responsible for the static we hear on the radio and that we used to see on old television sets. Nevertheless, this experiment demonstrates that the acceleration of a charge produces electromagnetic waves that propagate through space and can cause effects over a distance. A real radio transmitter actually uses the same process, the acceleration of charge, to create radio waves. However, rather than mechanically moving a charged object around, as we've been doing with the balloon, an alternating voltage is applied on an antenna. This causes the electrons in the antenna to move back and forth, much like the balloon, and thus emitting radio waves in the process. So, now you know that it's not just antennas that produce radio waves, but also everyday objects that have acquired a charge. Thank you for watching till the end. This video was sponsored by VidiTrack.